Okay, so what am I doing today? Oh yeah, equilibrium. Okay. Okay, so this is just an example of where I guess we use equilibrium. So the Haber process is what's known as the Haber process is the production of ammonia from its elements, so from nitrogen and hydrogen gas. Ammonia, I'm just talking right now. I'll be here in a second. So ammonia is used for a whole bunch of things, right? We use it for fertilizers, it's used in fibers, chemicals, a whole bunch of different things. The problem with this reaction is when you add the nitrogen and hydrogen together, I have this really small Kc value. What does that Kc value, small Kc value mean?
Favors reactants.
It favors the reactants, right? And the reactants are super favored here, and you can see this is at like 500 degrees Celsius, so even at a really high temperature, we are not going to produce a whole bunch of ammonia, but ammonia has a lot of like industrial processes, so that's just process. What we can do is manipulate equilibrium to produce a greater amount of ammonia, and so what we're going to be looking at here today is what's called Le Chatelier's principle, which helps us improve the yield in these equilibrium systems that don't automatically want to go into producing the products, into those quantitative stoichiometric reactions. So Le Chatelier's principle states that when a chemical system at equilibrium is disturbed by a change, the system adjusts in a way that opposes the change until a new equilibrium is reached. So whatever you decide to change in a chemical system, the chemicals react by doing the opposite thing, right? It's kind of like Newton, right? Every reaction, there's an equal and opposite reaction. Same principle more or less applies in these chemical reactions, and we'll look at these equilibrium reactions. So here's kind of a good example here. If I have a initial state of equilibrium between two chemicals, and then I add a whole bunch of one more, it's going to change until a new equilibrium is reached. That's all that that's saying. Did everybody have that? Okay, and so we're going to look at all of the different ways. We're going to look at all the different ways that you can affect the equilibrium of a system. Now, just because the equilibrium of a system changes, it doesn't necessarily mean that the equilibrium constant of a system changes. So just something to keep in mind. Okay, so let's look at all of this. We're going to fill all of this in. So if the concentration increases, what would happen here? I guess it depends on what we're adding here. But we'll write kind of general rules down, and then we'll look at more specific examples. So if the concentration increases, the system itself shifts to consume some of the added reactant or product. Shifts to consume some of the added reactant or product. So what that's saying is, like, if I increase the amount of nitrogen in that Haber process to produce ammonium, if I increase the amount of nitrogen, then the system is automatically going to have an increase in the amount of ammonium. So equal and opposite reaction. If the reactants increase, the system will respond by creating more products, or vice versa. If I have a decrease, so if in that same system, if I took out a nitrogen, the system would start breaking down the ammonia to replace that nitrogen that I took away. So if I decrease the concentration, the system shifts to replace some of the removed product or reactant. So there's like an increase. One thing increases. increases, the other decreases. Same thing here. Decrease. I'm going to skip to catalysts for a second. So if I add a catalyst to a system, does it change the equilibrium? Talked about it yesterday. Does anybody remember? It just speeds up the reaction, right? So there's actually no equilibrium shift. It will just increase the reaction rate. Okay, so temperature then, if I increase the temperature in a system, what the system will do is, so if I heat something up, the system responds by trying to cool it down. So it shifts to absorb some of the added energy. Then if I cool a system down, the system is going to respond by trying to heat itself back up. And so it will shift to replace some of the removed energy. Some of the removed energy.
So what do you mean on this concentration? You have like on the increase you have decrease, and then on the decrease you increase.
So if a product decreases, the amount of the reactants would increase, just inversely proportional.
Okay, I got you. That's referring directly to the product.
It's referring, to, and
I thought you were referring to the thing as a whole.
Then looking at the volume, assuming that we're talking about a gaseous system, remember the relation between pressure and volume. So Boyle's law, right? If I increase the pressure on a system and everything else is held constant, other than that, like temperature and the amount is held constant of like a balloon, if I increase the pressure of a balloon, the volume will decrease. And vice versa. If I decrease the volume of a balloon, I'll have an increase in pressure. So if I have a increase, now again, remember this will only work for gaseous systems. So if I increase, or I change the pressure by increasing the volume, I will have a shift to the side with the larger total amount, chemical amount of gas entities. And we'll look at a question. I find that just reading these two, just written form, doesn't necessarily always make sense. I find that if you look at an example, it makes a little bit more sense. So it'll shift to the side with the larger total chemical amount. So then if I decrease, I'd have the opposite effect. So if I decrease the volume, my system will respond by shifting to the side with the smaller total chemical amount of gas entities. few more like extensions on these rules, and then we'll look at them in application. What's up? Making a video. Say hi, friends.
Think of yourself.
Supposed to say hi.
Hi.
You guys better go kiss some serious butt, though.
I said it with you too.
All worried about me.
I love what everyone is.
Okay, so what is happening here? Ooh, that's not supposed to happen. That's in the wrong order. Okay, so if what am I doing? Okay, so here's an example. These weren't supposed to fly in. Pretend like you don't see them right now. Yeah, so if you increase the amount of nitrogen in the system is automatically going to respond by increasing the products. If you increase the amount of nitrogen, then the system would respond by increasing both the amount of products. We'll just have an equal and opposite reaction. If I decrease this amount, the system would respond by trying to increase it. They want to replace what's there. They want to keep that same equilibrium constant unless you change temperature. They're always going to aim for that same equilibrium constant. It doesn't change unless you change like concentration.
So then also if you try to decrease your N2, like your nitrogen and your hydrogen, it would do the same thing.
Yeah, if I took out a whole bunch of hydrogen, the system would replace it, would break down nitrogen and replace it. Yeah. Or ammonia, sorry. Alright, so what you have to write down here is changes in the concentration have no effect on the equilibrium constant or the reaction. We have to know how the system would respond to a change. We also have to know how it would affect the equilibrium constant. So for concentrations, they have no effect on that. They were just joking.
Just go to birth.
Give her a hug. Give her a hug.
Don't hug her.
I don't hug people. That's gross.
Yeah. Why are you on it?
She literally talks all day about how much she hates being hugged.
Bird handshake.
Risk high five.
Okay, energy is, the best way to look at energy is to include it in your reactant as if it was a product, right? And so remember from our thermochemistry unit, if delta H is, well, if energy is included as a reactant, is delta H positive or negative? Good thing I scheduled 2 weeks of review. If energy is required in the reactants, is the delta H positive or negative? Is it producing energy?
No.
So it's requiring energy, so it's negative. If energy is a product, positive. And so, if cooled, the equilibrium will shift so more heat is produced. And if it's heated, the equilibrium will shift away from the heat, so it will cool down. And temperature, out of all of the changes that we just looked at, oh, sorry. I thought it was on the same slide. Out of all of the changes that we look at, a temperature change is the only one that will actually, the only stress that will change the equilibrium constant. And so a change in temperature is the only stress that will actually change your equilibrium constant. So a shift towards the product side will, if the shift is towards the product side, Kc will increase. If the shift is towards the reactive side, Kc will decrease. which would make sense because if your reactants are increasing, your Kc value is small. If your products are higher, your Kc value is large. Oh my goodness, why is that flying in at the wrong rate? Okay, so looking at volume and pressure, again, remember those two are inversely proportional. As you increase one, the other one decreases. So an increase in concentration caused by a drop of volume, so if I decrease the volume, a shift towards the side of the equation, the shift will be towards the side of the equation with fewer moles. So, in terms of this equation right here, and I don't know if there's room, I would maybe write down this example, just underneath there if you have some room. So, in this example, right now, on the reactant side, because they don't give me any other information, I would just take the coefficients. So, there would be 4 moles on that side, and on the product side, there would be 2 moles. So if I decrease the volume of this system, my system will respond by creating more products. So they shift towards the side with fewer moles if you decrease the volume. If I increase the volume, it would be the opposite effect. Sorry, was everybody good? My bad.
Where is that 2 moles under?
The 2 moles, yeah, it should be under the products. Okay. So change in volume and pressure have no effect on the Kc value. The only thing that will change at equilibrium constant is a change in temperature. Also, changes in pressure and volume are only going to be a matter of gases, obviously. Last one then. Where's my slide that I want? Oh, just didn't highlight. So catalysts decrease the time required to reach equilibrium, but it doesn't affect the equilibrium position. So if I add a catalyst, nothing would change there in terms of the quantity of any reactant or product. It just lowers my activation energy. And so my equilibrium constant would also not be affected. So let's look at some graphical representations here. So for each of the examples, use Le Chatelier's principle to predict the effect of the change imposed on the chemical system, indicate the direction in which equilibrium will shift, and then sketch the concentration versus time. So in this equation, we're going to assume that we are adding energy, so I'm going to add heat here. What should happen? Would I have a shift towards the products or towards the reactant? I would have a shift towards the product side, right? Because energy is on this side, we just treat it as if it was a reactant. So the whole system would shift to increase the amount of water being produced. And so the equilibrium shifts to, how did I word this? To the right or to the products. Producing, yeah, exactly, more H2O gas. Okay, so the way that they like to represent these, all these Le Chatelier's principle graphically is I take whatever concentration, we assume it's at equilibrium, so we just draw a horizontal line, it's unchanging, and then we say, okay, we add energy, what happens? Well, in terms of whatever I'm looking at here, let's say this is the concentration of H2O gas. So it would be going constant, and then it would increase as that rate of heat increases, and then eventually you would reach another point of equilibrium, where it would be horizontal again. If I had, let's say, on the same slide, if I had the water, let's say at this, they were at initially like right at the same point, what's going to happen to the water? Yeah, it's going to, and then reach equilibrium. Right? No, it's fine. Okay, so the next one, I have water, which automatically, just, in my water bottle is breaking down to produce hydronium ions and hydroxide ions, even though it's just hydrogen ion there. And then I add a whole bunch of sodium hydroxide to my water. How is this system going to respond? How is the system going to respond? Like, no matter what, because I'm adding sodium hydroxide, there is going to be an increase in the amount, the concentration of hydroxide ions, right? Because I'm adding them in there. They will have to increase no matter what. But my system is going to respond, how so? Initially. Right, it will shift to the left. The initially equilibrium shifts to the left. Or the reactants. So if I had a whole bunch of water here, and, water is undergoing this reaction to produce hydroxide and hydroniums, no matter what. But at the point where I add a whole bunch of sodium hydroxide in it, what's going to happen?
It's going to go down.
The amount of water, would decrease. If you're looking at the amount of sodium hydroxide, right, if this was my OH, my OH would increase. And this would be the water, or the hydrogen or hydronium ion. Okay, so I'll put 2 here that I want you guys to try on your own. So just get right up there. That's so gross.
Oh, I plugged my ear on that one. Come on.
Oh, that's so gross. Okay, anyways, that was not my
I
idea.
had some of that fell
Rude.
on the chair
Perfect. I'm already sick, can't get much worse. Okay, so if I take this system where calcium carbonate solid, I already have energy in there, is producing calcium oxide and carbon dioxide. This system, we're assuming, is at equilibrium. The change they're going to do is they're going to remove carbon dioxide from the container. So what do you think will happen?
They'll shift to replace the CO2.
Right, so I'll have a shift to replace CO2, so that would be a shift towards the product side. In terms of the graph, if I'm looking at what happened just to the carbon dioxide, it would be at constant equilibrium, and then it would decrease, so it would decrease.
I thought it did.
They're removing carbon dioxide from the system,
Oh, I thought it.
right? So they remove it, it just comes out right away, so that you have this indicated by a drop in the graph. That's usually indicates that something is being added or removed, a vertical portion of the graph. And then what's going to happen? Is it going to go down or is it going to go back up? It's going to go back up, yeah, and it should pretty much reach that exact same line, right? I shouldn't go over, I shouldn't go under. It should reach the exact same concentration.
So I was right. It had increased kind of.
Okay, next one. I have acetic acid. It is going back and forth between its pure aqueous form and its ions. And then I add a few more drops of acetate. So what's going to happen? Shift towards the products or the reactants?
Reactants.
Right. Shift to... Wait, no. I added this. Products, yes, thank you. And so my graphically here, if I'm looking at the concentration of CH3COOH, it'd be at equilibrium, and then it would go up or down if I'm increasing it. Up, right? It's a nice vertical line, and then it would eventually come back down to the exact same concentration. If I'm looking at just the concentration of hydronium or acetate ions, originally the concentration would be low because this is a weak acid, and it would have a little bit of an increase and then come back. Okay, then don't change the page. Don't do it. I messed up on the notepad. I said don't. Okay, so here is a question, like a multiple choice question they could ask us. So they would give us this and they say, you know, out of all these options, what happened at point A, B, C, and D? So looking at point A in time, what do you think happened at point A in time? They added what? Right, because of this, they would have increased the H2 gas concentration, and the system responds accordingly. Yeah, like it would, NH would drop, this would go. Yes, at point B in time, does it look like anything has changed? So what might have happened there? They added a catalyst, right? Or sometimes they say you added like an inert gas. So you put something in there that's not going to react at all. Point C. What do you think could happen for C? No.
Well, the energy is shifting towards the products.
Because we have a change in both products at the same time, and then the reactant increase, what's happening here is we would have the gas is actually being manipulated. So I have is it a decrease? Shifting, that's a 4, then that's a 2. So this would be a decrease in volume, right? Yeah. Sorry, this is a decrease in volume. And the reason I would say that decrease in volume is because, right, there are 4 moles of this, 2 moles of this. So if I decrease the volume, they increase the amount that has the least amount of moles. And ammonia has the least amount of moles, so it would go create a whole bunch of ammonia and decrease the amount of nitrogen oxygen. The last one, D. What happened at D? There was some sort of a change, though. Did they increase or decrease the products or reactants? But did they actually add products or reactants at this point? No, because there's no like vertical thing, right? We also also didn't do anything in terms of pressure or volume because we don't have this similar change that we just seen. It didn't have a catalyst, so it probably has something to do with what? Temperature. Okay, so am I increasing the temperature or decreasing the temperature? How do you know? The thingies are going up. Well, this one goes down.
It's adjusting weight from the
Right, it goes away. So if I add energy, that means I would end up creating more product. So this would be an increase in temp. All right, so that gives you
You said products, but did you mean reactants?
where?
Because you said increase in temperature, and then you said so there's an increase, and you underlined the reactant, but you said product.
Oh, sorry. Yes, I meant what I underlined. Yeah, because we would just treat this as if it's a reactant. So if I increase the reactant, that means my system would respond by increasing the. I said it wrong again, didn't I?
You said the products.
If I increase the product, my system responds by increasing the reactants. Yeah, the opposite side. Do homework